Okay, and the last piece of the puzzle is, for energy that we're going to get into is friction. And friction with energy is conserved in our system if there's no friction. What happens to the energy when there is friction, and what goes on with that? Well, there's a simple little applet here. Friction does not destroy energy; it merely converts it into heat. And well, what is heat energy? Heat energy is, or thermal energy, more correctly, is just the internal vibrations of the atoms in a substance. So when I rub two surfaces across from one another, the atoms kind of rub into each other and they start moving faster and faster, and the temperature goes up. So that's all that happens to the energy, is it gets transferred to the vibrations of the atoms. And so that's what we consider as heat. And that heat doesn't stay in the book, and these are two books rubbing up against one another. As you see, the atoms start slowing down. That's as they pass their vibrational energy onto other atoms that they're contacting, such as the air and things like that. So energy is not destroyed if there is heat. All it does is convert it to another type. So we can think of our conservation of energy is slightly altered. Our initial potential plus kinetic equals our final potential plus kinetic plus however much thermal energy or heat was produced. So any energy that doesn't show up was just converted to heat, and that's what happened with it. So we looked at conservative forces before, such as gravity, Hooke's law with the spring, giving an object a push and getting it moving with kinetic energy. So when energy is conserved, it shows up as potential or kinetic. But friction is a non-conservative force. Not to say energy still isn't conserved in the universe, but it's that energy gets converted to heat and is allowed to leave our system. So here we've got a little more of a realistic roller coaster. We're starting with gravitational potential energy, and just as before, as it went down the hill, we're losing some gravitational potential energy and converting that to kinetic energy as it speeds up. But also, some of that energy realistically is going to get converted to heat, and again, it shows up as part of the puzzle. So when we have a roller coaster, it may not make it up the next hill, even if that hill is lower or the same height, because some of that energy is unavailable because now it's converted to heat. But again, notice that we still have the same total amount of energy that we started with. It's just some of it's in the form of heat. So this is why in roller coasters, every subsequent hill must be a little bit lower than the previous one, unless there's something that will do work on our roller coaster and give it some energy, such as that chain when it locks into that chain and gets click, 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 gets drug up to the top of the next hill. There, the roller coaster is doing work on the chain is doing work on the roller coaster and giving it energy. Anyway. But energy is conserved completely. That's not a lie. Energy is conserved, but we may have to consider the total universe, our system, as what we're looking at. So if this is my initial system of my universe, I've got 3 units of potential and 3 units of kinetic energy. After something happens, I might convert some of those kinetic or potential energy units into heat, but again, it shows up somewhere. It's still we still have a total of 6 energy units. Actually, it looks like I gained an energy unit, didn't I? Ignore this one. We created energy. Anyway, we don't end up with any more or any less energy than we started with in the universe. Unless you start converting matter into energy, which is what Einstein's E equals mc squared equation is about, but we're not talking about nuclear reactions here. So if we look at the entire universe, energy is conserved, but that makes the math a little bit complicated if we start looking at the entire universe. So normally what we do is we just look at a couple objects that we're interested in, and we kind of draw a box around them, and we say this is our system, and energy is going to be conserved in our system unless there's heat. And if there is heat, we may lose some energy. So we might have a roller coaster in the track as our system. We might have a ball dropping in the floor, and a floor as a system, or we might have a box sliding along a ramp, and that being our system. So normally we just look at a little bit of the universe. And if we start out with 6 units of energy, 3 of which are in our system, and then we convert some of that energy to heat, and some of that energy leaves our system. Notice energy is still conserved in the universe, but our system may lose some energy, and and that's fine. So work done against friction is going to be lost from our system unless we take into account heat. So if we do force times distance, where force of friction is our force, then that equals the energy that's lost from our system. So if we know the energy lost, we can, and the distance, we can calculate the force of friction. So here's an example of a system that we're gonna look at. We've got basically a ball rolling down a ramp. We're gonna leave the sun out of our system to make the math a little bit easier. And so here we've got a 2.4 kilogram ball, starts from rest and rolls down a ramp below. What is the system? We already said what the system was. Did the system lose energy? And what was the average force of friction? So you'll be able to tell when energy is conserved and when it isn't. If we're talking about losing energy, or we're talking about friction acting on our system, we're going to lose some energy due to heat. If otherwise, if we're talking about frictionless surfaces or elastic collisions, things like that, we're going to be conserving, our system's going to be conserved. So what did the system lose energy, and what was average force of friction? Okay, so we're going to look at the energy that we start with, and the energy that we start with is going to equal the gravitational potential energy of this ball on a hill. So mgh. So 2.4 is our m. G is 9.8, and our h is 12 meters. Okay. Then at the bottom of the hill, we're going to lose all of our gravitational potential energy, and we're going to convert that energy into kinetic energy, and it sounds like we're going to lose some to heat as well. So our initial potential energy, we said, was 2.4 times 9.8 times 12, so 282 joules. At the bottom of the ramp, we don't have any gravitational potential energy, but we do have some kinetic energy. So that was 2.4 times the velocity, 11 squared divided by 2, so 145 joules. How much energy was lost? Okay, quote unquote. So we lost the difference between that, which is 137 joules. So that is the change in energy. That is the energy lost due to friction, which is going to equal the force of friction times the distance that the object slid or moved. And looking at our picture, the diagonal is the distance that the friction was acting on. So that's the distance that we want to use as our distance. So 137 was equal to the work done by friction, which is equal to the force of friction times the distance, which is the diagonal, 22.5. And we get that the force of friction was 6.1 newtons. So just an example using friction. One more example, friction. This will be kind of a shorter, which would be good, shorter PowerPoint presentation, which would be good because the last one was a little bit longer. Sorry about that. So here we're going to push a crate from rest. We're going to push it up a ramp, a distance of 22.5 meters with a force of 15 newtons, and it's going to come to a stop at the top. What's the system? The system is going to be our crate and our ramp. We're going to ignore the sun again to make the math a little easier. How much work was done? Well, we exerted a force of 15 newtons times 22.5 meters. So that is the work. So so we do 15 times 22.5, 337.5 joules. So if we don't lose any energy, then we should have 337.5 joules of energy stored in our crate when it's at the top of the ramp. Okay. And next it asks, how much energy did the crate gain? Well, when it's at the top, it comes to a stop. It's going to have gravitational potential energy. It's not going to have any kinetic energy, or there's no springs going on. So let's figure out how much gravitational potential energy it has. 2.4 is the mass times 9.8 times 12 is the vertical height. So 12 is the vertical height. And we get 282 joules. So what doesn't show up must have been lost to heat. Okay, so the difference between those is 55.3 joules of energy. And the next question is, what was the force of friction? Similar to the last problem. Well, the work done against friction was 55.3 joules. That's going to equal the force of friction times the distance over which it acted. That diagonal is still 22.5. So we get a frictional force of 2.46 newtons. And that is it for energy. There's still plenty more to be learned, but that's where we're ending our topic. So good luck, work on the problems, and study for the test.